All right, I guess we're at time. I'll begin. All right, hello everyone. Welcome to our TRC Shop Talk. Today we're going to be talking about the beyond the data sheet real world examples of what we do to solve power electronics problems. And joining me today are three amazing engineers that have worked with TRC for quite some time. Tom Denny, who's been with us for almost 4 years. Nick DePaolis, who's also been with us about 3.5 years, and our newest member, Jeremy Ha, who has joined us a little over a year ago. And these guys are always working with various types of, either it's different industries or different types of products, working with our customers, our engineering customers, and becoming part of their engineering team to solve power electronics problems. Today, we're going to show you just a couple of about 5 different types of individual solutions that we have solved over the last few months. And if we could bring that slide across right now. So today we'll focus on inverter requirements outside the normal range. These are inverters that we are working with, and they don't quite fit the application without some type of modification, so we'll share that. We have a large number of power supplies in a tight installation. This is an interesting one where we can demonstrate what we've done with power supplies that we sell from our partner, but also some TRC engineered solutions we created behind the scenes. We have an audible noise restriction. This comes up quite a bit with fan-cooled power supplies, and we'll show you how we're able to reduce that audible noise. Back EMF is one of our favorites, and this comes up a lot where you're dealing with types of motors or solenoids where the power supply will experience some energy or kickback, and we'll talk about that one. And then finally, leakage current limits and corrosion environments, which also is becoming more common as inventions get to expand beyond just the inside the office space. So with that, let's begin, and let's talk about the inverter application. This is something that Tom was actually working on for several months with a client. And Tom, just to elaborate in terms of how you were able to work on this inverter.
Sure. So this client was using a pretty standard military battery that you see there in tan, and they wanted to charge them at the maximum voltage allowed by the battery, which was at 33.7 volts, get the maximum amount of power out of the batteries. The problem is that most inverters cannot accept, at least most 24-volt inverters can't accept a voltage that high. No standard off-the-shelf inverter they could find was able to do it. So a couple things that we knew about the project. We knew that they wanted to be able to run their equipment when the battery was between 22 and 33.7 volts DC. They needed to output 120 volts AC from the inverter. You needed a minimum of 3 kilowatts. And so we came up with, well, one of the things we looked at least right off the bat was the NTN 5K-124. This is an inverter with 4,000 watts of power at that input voltage. Input could be between 20 and 33 volts, so it's close. And it did output 120 volts AC. So it was close to what we needed, but just not exactly what we needed right off the shelf. Go to the next slide, please, Ty. All right, so what we did was we ended up doing a little modification here. So we confirmed with manufacturer that a 33.7 volt input was within the tolerance of the inverter. Even though it was only rated up to 33 volts, when we looked at the test reports, they'd been tested at a higher voltage than that. And so we were able to get 33.7 volts in there without causing any damage. So we had a custom firmware created where we changed the shutdown voltage. So that normally, if you applied above 33 volts to this inverter, the entire thing would shut down. So when the customer was taking the batteries right off the charger and putting them right into the inverter, even though it only had that, it was up there at 32.7 volts for a moment or two before it started discharging, it would shut down the inverter and then it would no longer, discharge. So we're able to change that shutdown limit to 34 volts DC. Then there was a whole nother issue with the overvoltage alarm, um, because even once we changed the shutdown voltage, the alarm was still going off like crazy, anywhere above 31 volts. So we did some Modbus programming there to change the overvoltage alarm and made that 33.9 volts. So now when this client connects the battery, the the inverter starts working right away, doesn't shut down, no alarm, and they're pretty happy with it.
Yeah, and this was an interesting one because, well, first we had to assess the customer's situation, and I believe, Tom, you went to the client a couple times to actually get all the parameters necessary, and then also make sure that we were able to communicate with the factory, because typically now you have to work with the constraints of the factory and making another version of software or firmware in this case to be able to be used and tested. And Tom did a lot of that testing along with the factory, not just with the customer itself, but with the factory to understand that, okay, this was an actual valid firmware. And eventually, Tom, did you go visit the client and actually implement the firmware there?
We did, yes, yeah. We did a couple trips back and forth to the customer. As I said, the whole overvoltage thing was ended up being a separate issue, where I guess only the newer uh, models of the NTN 5K had the ability to change that overvoltage alarm. So we had to get a unit that had that capability and then install the firmware on that unit and then make the Modbus change after the fact.
That's great. So here, just one example where this is a little, this was not something common for us. Most of the time, our stuff is analog. In this case, we actually did firmware modification and we took it to the customer.
It's
The
pretty
next,
it was
go
pretty
ahead.
neat. I was going to say, I mean, on the left there, you can see the actual NTN 5K opened up there. There's actually three MCUs on there, three different boards, three different little computer chips. Only one of them actually would control the voltage shutdown, the overvoltage alarm. So we only had to update firmware on one of those MCUs. But yeah, a lot of computing power going on inside there.
Yeah, this one was an interesting one. The next one that we want to bring up is a tight installation, and in this case, this was a really aggressive project. Nick, can you just walk us through how we were able to solve this?
Sure, absolutely. So, to kind of give you an overview of the project, we were essentially tasked from the customer with providing them a 12-volt system that could deliver up to 16,000 watts of output power, 16 kilowatts. The device itself, or the enclosure, which we later found out, was going to be deployed in a confined service access way. And it needed to be installer focused. And what I mean by that is that the power supplies that would be installed inside this box had to be both removable and serviceable in place. They couldn't take this thing off the wall and bring it out. Once it was in, it was in. The installation was also partially exposed to various environmental elements or conditions, specifically dripping water. And then our timeline, it was very compressed, as Mike kind of alluded to there. And it was basically we needed as soon as possible, if not immediately. So that kind of contributed to the kind of the engineering constraints there. Overall, we knew that based on the power and the voltage that they had provided to us, we knew we are going to be using some large cable, specifically 1/aught cable. The dripping water presented its own level of risk in doing something like this. These power supplies, they don't do well when you have water on them. So we wanted to make sure that whatever we did end up designing, we would not only protect them from that water, but also reduce the risk and try and mitigate, based on our material selections, any risk of galvanic corrosion. Basically, those dissimilar metals reacting with each other. Additionally, structural support would be required for this just because we're going to be putting a ton of weight on the wall. And that is also in addition to the cable strain because we're running a ton of wire on this thing. So if you go to next slide, please, Kaya. So essentially, what we did, kind of a little clever way we kind of figured a way around this, was we utilized the existing mounting holes on the power supplies, and we made up our own little custom hinged bracket to essentially swing out the power supplies. So the hinged base plates would go into the enclosure onto the actual body on the wall, and then when you need to make your connections, swing it out, put the wires on, swing it back, bolt it down, and it's done. This basically enabled that access for simplified wiring and servicing by those technicians, while also maintaining that clearance within that constrained access way, like that envelope, if we call it.
Yeah.
Go ahead. Go ahead, Mike.
No, and just the whole reason why we were able to be successful, I think one of the major reasons we had access to talk to the installer, the actual installer doing the installation, and relatively about 3.5 months before the install. And what an installer was able to do is actually walk us through a 3D rendition of the installation site. The installation site rendition gave us like the real feel as to, okay, what is that installer actually going to be experiencing? And that's where the hinge brackets came in. It was more for how do we get that installation done fast without having the installer have to go into the clearances, try to get tools into the box while trying to put the power supplies together.
Yeah, absolutely. I think the main reason why we were able to meet that accelerated or compressed deadline is because we maintain that continuous communication, not only with our factory manufacturing it and also the field installer, is because since we had that increased visibility on that scale, that digital model of the accessway, prior to fabrication, we were able to validate all of the different spatial constraints, the serviceability, before we even actually made the physical being the prototype. We were basically working with the client so close that we were able to align that final solution with them prior to even bending the metal, which was really, really rewarding to see.
I think we have one more picture to show that
Yes,
actually
go
shows.
ahead. Switch it up right there. So that basically is that 3D rendition we talked about. That's the fully custom engineered solution. We had that fixed 16-week delivery window that didn't have any flexibility, and that execution to provide them this solution was fully dependent on both the precision planning and coordination that we had together.
And that was really, I mean, it was tight job. Definitely, we had to really stretch ourselves, but it was ultimately at the end to see it actually in production and working was a really great feeling for us. So the
Mhm.
next one, I think this one's Nick as well.
I'm back
Where
again.
we have quiet power requirements. So Nick,
Yeah.
walk us through this one.
Yeah, so essentially, a lot of clients, you'll see this come up from time to time, where with anything that's fan cooled, it just inherently makes a noise. And depending on the application, that could be okay if it's sitting in a closet somewhere. But if it's going to be anywhere where people are hanging around, it's going to get annoying really quick. So essentially, the client came to us, they were experiencing these excessive audible noise issues from their fielded power supplies. The requirements they had basically were to provide multiple output voltages within a single chassis. They just wanted it quieter. Now, the issue they had is there was no ability on their end to redesign, replace the power supply platform, and they were kind of stuck with this Meanwhile NMP series. So what we had to do essentially was to see, okay, what options do we have to reduce the noise without, requiring recertification of the system, without taking down their systems themselves and causing these massive service outages. So what we found was essentially that we worked really close with the manufacturer at the factory level specifically and found that the fan speed profile is governed by their embedded microcontroller, like the firmware. The units that the client currently had this aggressive fan ramping characteristic, and that was due to their legacy firmware and the legacy fan. Working with the factory, we identified that there was a compatibility. We had some compatible updated firmware revisions that we could apply to the unit, and we also had to swap out a fan. So it was an NMB fan specifically that had this improved acoustic profile. Now, even though we're swapping out that fan, which is listed under the CB report as a critical component, Meanwhile, had it already certified, just listed as an alternate, so we didn't have to go through a whole lengthy and expensive recertification process. And since we are actually a Meanwhile service center, if you want to go to the next slide, Kaya, please. We actually are able to fully, disassemble the thing, take all of the guts out, do the actual firmware upgrade, and provide the client with a seamless solution. They just send us back those old units, and then we would go in, take it apart, swap the fan out, wipe and flash the firmware, and basically deliver it back to them in short order. Everything happens here in the US, and we can expedite that shipping, so they were not without product for very long at all.
And
Essentially, oh, go ahead, sorry.
go ahead. I'm sorry,
Well,
Nick.
I was going to say the way we also provided this was essentially we provided them an initial batch of the upgraded units with supporting test data that we developed in addition to the factory. We worked with them to develop our own in-house validation to get the client's buy-in before we started upgrading all their hundreds of units. So what that basically looked like was we took a non-modified unit, took baseline measurements with an uncalibrated, decibel meter, and then we compared that to a modified unit, several of them to kind of build up that control group versus the test group. Provided that to the client, as well as several units we did upgrade, and they performed their own, independent validation testing to see if this was actually going to be a good fit for them. Installed some of them in their current field deployment sites. We had great feedback from their customer. So then that's when we rolled out we call it almost like a phased upgrade process, where we would basically take in manageable batches and kind of cycle out their currently fielded units so that they didn't have any major outages throughout all their fielded installations. It was pretty seamless.
And it's interesting, over the last 12 months or so, firmware adjustments have been more commonplace for us here at TRC. And these are just two examples between Tom's and Nick's, but we've had several others over the course of the last several months, because again, the modifications need to be made. And when you have these types of power supplies and a team capable of doing it, it proves to become a faster solution to the client. All right, let's switch gears and talk about some classic things that come up in the industrial control sector, and this is back EMF. This was a recent situation we had with a client, and Jeremy Ha was involved with this one. Jeremy, take us through this one.
Yeah, this was a good one. So for this project, we had a client who was working on a project for their industrial control system, and they were essentially just having issues with back EMF. And to give some context regarding back EMF is defined as a voltage spike or voltage backfeed that's produced by inductive load. And that voltage opposes the source voltage. This is very common in electric motors, and generally that will cause the unit to go into a protection, typically over voltage protection. And so what was happening in our client's application was that they were decelerating their motors on their assembly lines, which resulted in a backfeed to their power supplies and caused it to go into over voltage protection. Typically, there are two methods we implement to protect against back EMF. The first is to deploy a diode configuration. That consists of a blocking diode and a flyback diode. And we put down the output to protect the power supply from the backfeeding. The second method is to have a power supply that has built-in protection for back EMF, which makes design integration a lot simpler. And we commonly recommend the first method of blocking diodes for designed-in systems where introducing a new power supply is a lot more difficult. But for this project, Kaya, if you want to move to the next page, we coincidentally had a new product coming out as part of our offerings that did have built-in protection and was easier to integrate. It wasn't exactly advertised for the specific series, which is the XDR or XTR series, but we did confirm through the bill of materials that the product did have caps and FETs with high voltage ratings that provided their 24-volt system with up to 35 volts of back EMF protection.
Yeah, and this one was interesting because the client was evaluating another solution that was specifically marketed for back EMF protection, but this product actually performed much better. And as a result of it, I know Jeremy is going to be writing an application note in the next month or two, because this is something that does come up a lot in this field, and this product will definitely be able to help multiple clients as we move forward in more designs. All right, excellent. Last one is leakage current and environment. And this one was interesting because it's something that we don't really think about too often, but it's a gaming system that, think about an arcade, like the picture here, but where the arcade may not necessarily be in a closed air-conditioned environment, let's say 12 months out of the year. It could be an open air arcade where the elements from the outside can come in, specifically salty air, let's say a boardwalk or a beachfront type of a situation where you have a lot of salty air environment that now enters the building, but also enters the electronics, especially when you have fan-cooled systems. In addition to that, the client was also working with the agency to pass a leakage current test. The issue was that there were multiple power supplies installed in the gaming system. You can just imagine you have different functions, and they opted to go with multiple power supplies, and that resulted in increased leakage because every single one of those power supplies have a leakage current to ground. On top of that, they had a medical EMI filter, which helped a little bit in terms of reducing the EMI and contributed a very small amount to the overall leakage, but it still became a problem. Now, top that with, now they have to go through a humidity test because of the environment that they're in. Well, what happens during a humidity test is leakage current tends to go up. Somehow, through the creepages of the power supply PCBs plus whatever else is in there, that leakage current finds a path through that moisture and increases that leakage to ground. So this became a real problem for the client. So one of the ideas we had was, well, let's use a modular configurable power supply, because in a sense that would be one AC input. So we would only have one AC leakage path and then multiple modules to address all the different functions. And that was a consideration. The other one was we'd have to also find a way to make those the products conformally coated. So because when you have conformal coating on those PC boards, at the very least, that will minimize the corrosion that would be associated with the electronics. So if you look at the next slide, what we were able to find was we recently launched a new product from Meanwell called the NSP series, and an NSP 320 and 200 combination was a perfect solution for a couple of reasons. One is that the product is medically certified, and the leakage current for every single power supply is about 350 microamps or less. So if you had multiple of those units, you obviously had less leakage current to contend with. In addition to that, these products are also conformally coated from the factory, so that provided the immediate protection that the client needed. So 3 individual power supplies in the system was able to reduce the leakage current by 75%. And also the conformal coating of that product just made it a no-brainer to get installed in. Now, the NSP series, specifically from 75 watts to 750 watts, all have medical certifications and conformal coating. And this customer is extremely happy. They were able to actually switch to this product almost immediately.
So Mike, leakage current. So we're talking earth leakage current. So it's based on what the capacitance to ground, right? Between the AC input and ground.
Yes, actually, the most common point is the common mode capacitors that are usually in the input filter to ground.
And
So if you think about it, you have both line and neutral, and
right.
the impedance of those capacitors over a frequency allow them to conduct to a certain point, to a certain level.
And I guess
It-
like as you put more in parallel, you're lowering that impedance basically. You're putting those impedances in parallel, lowering that
Yeah.
impedance. So the more you have in parallel, how many can you put in parallel and still kind of be within limits here?
On the power supplies
Yeah, yeah.
themselves, well, in this case, on the NSP at 350 microamps, you put about 5 or 6 of them and
At least I
still
guess.
be able to be under the UL limit.
But that's because of that low medical leakage.
Exactly, because their filtering has less, let's say we call them Y capacitors, and more inductive filtering, which is in series with the line, that allows for the EMI filter to work, but yet not have as much conduction to ground.
Right. It's medical grade leakage, but they're still industrial rated power supplies. So they work for this
Yeah.
application. So they have
As a
both.
matter of fact, yeah, and this product here actually has certifications for industrial, medical, household appliance, and also the 61010, which is the industrial test and measurement
Oh, that's right. Yeah. Yeah.
standard. So quite a good solution for us to be able to help these clients.
Nice.
All right. Well, this concludes what we have in this shop talk. But before we go, this is an opportunity for us to also open it up to the ones that have joined us, if they have any questions about what we shared at all in some of these applications, or if there's an application you have that you would like to discuss at this time. All right. Well, if that's all, before we go, one thing in terms of if there's anything that you found interesting here, you want to have any further discussions about this or any other application, our number is 888-612-9514, and sales@trcelectronics.com will get you to the right contacts, including us here at engineering, if you have any technical questions. Thank you all for joining, and hope to see you on the next Shop Talk.